Hello, today I'll be talking about how RL or reinforcement learning works and how it is different from most other machine learning models. What reinforcement learning is a model that learns from the state and actions that take place. You can think of this like teaching a child with your rewards. If you tell the child don't go and touch the stove because the stove is hot, and the child goes and touches the stove, there is a outcome that is not only painful to the child, but there's no sort of reward for doing so. It is just a negative experience. If you were to say to not touch it, and then the child never goes and touches it, you might see a reward given to the child, whether that be a piece of candy or some sort of toy or any other mechanism that would be used as a reward. That is the same idea behind reinforcement learning. You give the model a input or an action and its state that it is in, as well as a future state that will take place, and what reward would happen based upon what the model does. What this does is it causes the model to continually learn and try to exceed its reward that it got previously. Its entire goal or purpose is to have a larger reward. This is something that is different than your normal machine learning, as it in of itself is the thing that is doing the learning. What this is not being told a direct answer, but taking actions and seeing results based upon whatever action was taken. What I'm going to do is I'm going to be talking about this cart pole and the idea of this cart pole project in and of itself is just a environment to learn any sort of reinforcement learning. What this does is you've got an agent that you can see here in the diagram is moving this little black box, which is what we call the cart. And it can move to the left or to the right. Those are the two actions it can take. And the goal of this, or the reward values that are associated with it, is keeping this pole upright. There's in this documentation some values around what the goal looks like and sort of when it ends or it doesn't end in terms of its degrees for the pole. But generally speaking, anytime that this is staying mostly upright, that is considered a win for this. And there's a time aspect to this of how long this is staying upright, and that's what the reward is based upon how many actions are taken over a set period of time, and that's what gives a reward value to this. It's a pretty simple idea, but it's a great example of how reinforcement learning works. So, getting into what reinforcement learning is, what we can see here in this diagram is we've got this state attribute, and from the state we go and take an action. Based upon whatever the environment's in at that point in time from that action, there is a reward that is sent back to the model. Then from there, this continues on and on and on in order to have the model see, based upon my initial state and the action I took, so in this case, moving the cart to the right, I got this result. Either the pole is standing up still or it is fallen over. And so based upon that, it's going to give a reward. Now, we don't want this to be something where it's immediately, okay, yes, done, I've got the answer, I'm good forever. It's something we want to maximize over time. And what we can see within our cart pole example is that the value will continually go up. In the example, we can see our average reward here and our maximum reward that was achieved from the model. We can see that we got about 250, which in this case is good because we've assumed that 200 is a winning condition. And then 384 is the max reward that has been received. So we can see here in the model that there are some times that it actually doesn't succeed. In episode 15 here, the reward was actually below 200, which means that our model did not solve the problem. But being that we care about averages, we would say that this is fairly good for this example. The key thing of how these reinforcement learning models work is based off of this equation here. This is called Q learning. What it does is it takes a function Q given a state and an action, and what it does is it tells us how good that action was. It follows a Bellman equation, and what we have is a value of an action, which is its immediate reward, plus a discounted value of the next state. So we have this gamma max, and again with the future state and future action from that. So what we do is we approximate this Q function with a neural network in order to have it be something that is quicker to actually generate rather than manually generating a Q table, which would be very computationally intensive. So what we have is deep Q learning, or DQN, which is a neural network that approximates what those values in the Q table would be. So instead of updating from an experience at a time, we would store our transitions in this replay buffer, and then we would train on those random batches. What this does is this breaks correlations in the data and it stabilizes learning, is the idea at least. We will talk more about some of the problems with this later on in this video. The next key point of this is exploration and exploitation. What we've got is we need to have the model be able to explore different possible actions that it could take in order to get different possible rewards. And then we also need a way to say, okay, after a certain time, you should have learned something. You should learn how to do this problem. So we don't want to just continually throw random stuff at it in order to see if we hopefully solved it, because that flatlines over time. And I'll show you in the terminal some training data of where that does flatline, or it even can oftentimes get worse. So what this is a epsilon greedy strategy where the agent sometimes is going to take some random actions, and then after that epoch decreases, that epsilon value decreases, we'll eventually get to a point where it's more following the greedy exploitation route here. And one of the things I noticed here in my function for the epsilon decay is that when I had epsilon decay at a higher value, if I had this at about anywhere from 10 to 20,000, it was pretty unstable in what it generated. Um, I also started with an epsilon end of 0.05, which generally meant there was a 5% randomness that took place. And this thing was not able to solve the problem even close. It would sporadically get above 200, but on average it was in the low hundreds. And so you'll find that if you change your epsilon end and then how quickly your epsilon goes to that epsilon end, you're going to end up with different rates of how this model learns and the randomness to the learning that takes place. Part of this instability that I had was, even though I had a replay buffer, the DQN would degrade its performance. So as shown here in the terminal, this is a training that I did with an epsilon value of 10,000. And we can see that as it's starting off to build, it's in the low under 50s for its reward values pretty consistently all the way until about episode 200 to 250. That's when we start to see some good values. Like we can see here that the epsilon is 0.001, so we're basically got no randomness in this. But we are getting a good reward value, and pretty consistently we're getting some good reward values here throughout. But as this continued and it moved closer to the 300s, these values started to shrink with time. You can see here we're starting to get into the 130s. Then you can see now we're in the 110s pretty consistently. And it kind of hovers between 110 and 130 until we start getting towards the end and it starts to go back up a little bit, a few of them at least. So this is something that I had to debug and sort of tweak some of the epsilon values, epsilon decay, and more importantly, what I added was a double DQN. And what this did is when this ran, I would run it into the DQN again in order to help decouple actions and selections from a value estimation. And this would reduce over optimism. All it did was improve the stability. It made the values actually start to become successful on average. And that's one of the things that is kind of a hack that you can do for DQN, but it doesn't solve the full stability problem. Another thing that works fairly well for DQN is having a stop time. Being that we can see really all of these episodes here, anything past 250, nothing was getting better on average. What we can do is we can have a stop function essentially. And that's what we have here is we're tracking our average reward over a window period. I chose 50 iterations or 50 episodes. And then it will save that to a new model. And then once we get our average above that 200, we can just close. We can just end our run on the model training. Otherwise, if we don't get that, then we'll just save it as a different model. That is something we can look at as well and run evaluations on. With evaluations, what we have is slightly different than how we do training. With evaluations, we don't want any sort of epsilon values at all. We want it to be completely not random. We want it to be completely known every single time running the model. So that's one of the big distinctions is when training, we purposely put that randomness in order to try to have it try different things and see how well it can respond to that. But in evaluation, we don't. And so what you can see is evaluation is running the model just like you normally would run the model, but not injecting any randomness to it. What this does is we get to have a clear picture of what the agent has actually learned rather than by some off chance, due to this epsilon, we got a high number. And that happens all the time during training. There will be spikes anywhere from a low value all the way up into the hundreds when in training. Like, for example, we've got a good value here where we were at mostly 177, but the episode right before that was 292. That's a big difference between the two. So our evaluation, we want it to be consistent and deterministic. What I did with this, just so that we could get an idea of how this works, is I put a fast API and Docker build up with a web UI to kind of diagram how this model works. And it's really just essentially showing a visualization of how the model would run. So we can see here on this last run, we had a total reward of 229. And on this run, we can see that, well, in this case, we actually didn't solve it because we're below 200. But running this different amounts of time, we can see that it was much better on this run, really keeping that super tight to the cart and making sure that that does not fall down. But that's just a visualization to show how that reinforcement learning is taking place. So the big takeaways from this project and the key things to know about reinforcement learning is that learning can be very noisy and unstable in comparison to other types of model trainings. You've got a lot of intentional randomness that takes place in order to try to have the model learn and find a good path that it should consistently take. Your exploration scheduling matters. Having your epsilon decay and your epsilon end set well will impact how your RL model works. And it's something to keep in mind. Your evaluation, you need to make sure that when you're evaluating, you're keeping all of that randomness out of it and you're truly taking your model against what the actual problem is to make sure that the model has actually learned something and it is actually consistently good at what the task is. And when you're deploying an RL system, it's not something that is a normal kind of deployment that takes place. Some examples and how this is deployed and used is in robotics. When you've got a robot that is defined to do a certain task, you might have sensors or cameras or other kinds of input that is verifying that the robot is doing what it actually is supposed to do. Another very common new way that RL is being used is specifically in what is called reinforcement learning with human feedback, or RLHF. And what that is having a human in the loop in order to help guide the RL model and make sure that it is as good as it can be or meeting and exceeding in the task that it is set to do. It's this is really not something similar or really used in your traditional LLM or anything like that. That's a generator or a transformer. These are generally built for very specific tasks and they're good at completing those specific tasks. If I tried to use this RL model in anything except this cart pole, it's not going to be of any sort of use. It's not going to be something that is functioning outside of the cart pole example specifically. So a lot of these things that exist in the DQN side of RL learning are something that has been well documented and studied, and there's other algorithms like PPO that exist in order to abstract a lot of this and make the model more definitive and not have the same errors with the kind of exploration and exploitation, as well as all of the Q table issues that you might run into with DQN. So what I'm going to do is I'll post the repo to this so that you can go and explore, and you can go ahead and try any sort of other epoch values that you would like. And that way you can try different ideas and see what works best in order to get the best training model possible. And I highly recommend that you research reinforcement learning and try to build something like this from scratch. It's a very challenging approach versus just a simple neural network because of all of the different hacks and exploits you kind of have to do in order to get something good or decent out of this. So in the next video, I hope to be going over some PPO algorithms, and that way there is a comparison that we can have against the DQN. So thanks for watching, and I hope you learned something about reinforcement learning.